Today we're going to talk about electromagnetism and right-hand rules. I'm sure you've heard of electromagnetism before. We're going to save right-hand rules for later because that's new. But it was discovered in 1820 that when a compass was placed near a wire that had current running through it, an electric current running through it, the compass would deflect, or it would be affected by what seemed to be a magnetic field. So we're going to do a few experiments. Hopefully that's actually what we find. When I turn on the voltage source, you see that the compass suddenly flips around. Okay, that means that there must be a magnetic field in the area because a compass is only affected by a magnetic field. So if we move this compass around this set of coils of wire, we can see that it acts just like it would if we were moving it around a bar magnet, let's say. It tells you that one of these ends is a north pole and one of these ends is a south pole. Okay? Now, we know that the south pole of this compass points toward the north pole of the magnet because those two things are attracted to each other. Opposites attract. And we know that the north pole of the compass points toward the south pole of the magnet because opposites attract. So that means that this thing acts like a magnet with a north pole on this side and a south pole on this side. Now this thing is called a solenoid. It's got coils of wire piled on top of each other. So this is a triple layer solenoid. It's got one set of windings and then it's wound back and wound over again. Okay, so this is a triple layer solenoid, which makes it a bit stronger than some other kinds of solenoids, but we'll talk about that later. So since this thing acts like a magnet, it's called an electromagnet. It's a magnet that's made by running electricity through wires. That's an electromagnet. So it should have certain other properties as well. It affects a compass, and so it should also exert a force on bar magnets. So we said that this is the north pole and this is the south pole. So if I try to push another north pole into this side of the solenoid, this is hollow, by the way. If I try to push a north pole into that side of the solenoid, it gets rejected. It's a repelling force, right? Like poles repel each other. But if I try to put this south pole in, it gets sucked into there. Okay, opposites attract. Another thing that we should expect if this thing actually acts like a magnet is that it'll have an effect on ferromagnets as well. Those are materials that are not normally magnetic on their own, but can be made magnetic when placed in a magnetic field. So if you remember these things, they are steel bars, not normally magnetic on their own, but they should be made magnetic if placed in a magnetic field. So let's try it out here first of all. If we can line these things up with the magnetic field, they should attract one another. Well, it seems as though they're not really. Okay, but that could just be because the field is too weak out here to actually line up the domains in these two ferromagnets. So let's try it on the inside over here. Well, it's not very dramatic, but if I put one in on both sides, I can feel it pulling. If I put one in on both sides, they're attracted to each other suddenly. The domains have lined up, and now these two ferromagnetic materials have become magnetized. So if I try to pull them apart, it takes a lot of effort. Okay, and if I crank the voltage on my voltage source a little bit higher, hopefully without causing damage, it's a bit more dramatic. Pulls it in, and then it's just really difficult to pull them apart. No, can't do it. So electromagnets are actually really useful. you can control how much magnetism there is by changing how much electricity you're running through the solenoid. And that's useful in a whole bunch of applications. Think of use at a junkyard. If you need to pick up old burned out skeletons of cars, they're pretty heavy, and so you could use a forklift, but many places use electromagnetic cranes, which is really nice because you can turn on the magnetism when you need to pick up a car, and because it's so strong, you can do that. And then when you need to drop the car, you can turn off the magnetism, turn off the current, and then the magnetic field ends and drops the car. So electromagnets are a very useful piece of technology. Now let's just try one last thing. We're going to change the polarity of the solenoid. Okay, so this, just so you know, this was the negative pole right over here, and this red one was connected to the positive pole. So now we're just going to switch them. Okay, so now we've switched them. Let's see if you can remember what direction things were happening in before. Okay, so before this was the North Pole and this was the South Pole. Now it has changed. Now the North Pole of the magnet points to this side, which means it's the South Pole of the solenoid. And if we flip it around, we get this is now the North Pole of the solenoid. Okay, we can also test with our bar magnet. If this is the South Pole of the solenoid, it should suck this in. And so it does. And it should shoot this out. Now we don't need to do this part because it's already proven, but it's just so fun. Now, that tells us that the direction of current flow determines which is the north and which is the south pole of the solenoid. Okay, so electromagnetism, the magnetic field produced by a current, is going to depend on the direction of the current. And that's going to bring us to right-hand rules. So we saw that the movement of electric charge, which we would call an electric current, produces a magnetic field, and the direction of that magnetic field depends on the direction of the current flow. We did it using a solenoid, which is a set of coiled wires, but it also actually works with a straight wire. So if you think of the wiring in your house, it's either running vertically up studs in your walls, maybe it's running horizontally through joists in your ceiling or in your floor. You're also going to get a magnetic field produced by those wires. It just looks a little bit different than the one that's produced around a solenoid. So if you look to the right over here, we've got a wire in a very bad photocopy. A wire is oriented vertically like this, and it says that the current is traveling upward through that wire. Now you're going to get concentric circles. That's what the field looks like. Concentric circles that get farther and farther apart as you move away from the wire, because that's what happens with field lines, that as you move farther away from the source of the field is going to get weaker. And so then we show that by using field lines that are farther and farther apart. Okay, so that's what the field is going to look like around the wire. Of course, it's three-dimensional, so it's not just at the very base of the wire over here, but the field is being produced all the way up the wire. Okay, so we get these concentric circles, but they also have a direction to them. A compass, if you would place it around this wire, would point in one direction the entire way around. So as you move the compass around the wire, it's going to continue pointing in the same direction all the way around. Okay, and that's what this diagram just below here is supposed to help you with. So this is for right-hand rule number 1 for a straight current carrying wire. So here's what we're imagining. There's a wire that's sticking out of the page. This might be hard to imagine, so see if you can do this. There's a wire sticking out of the page. And these field lines here are the concentric circles that we were talking about. And they get farther and farther apart as you move away from the wire because the field is getting weaker and weaker. So we can figure out the direction of the field using right-hand rule number 1. So here's right-hand rule number 1. You take your right hand. That's important. That's why it's called the right-hand rule. Right-hand rule number 1, your thumb is the current flow. Okay, so if the current is flowing upward, your fingers are going to curl in the direction of the magnetic field around that wire. Okay, so if we're looking at it like this, and your current is flowing upward, then if you would place a compass in this field, it would point this direction. It would point along my fingers. And as they curl around, so would the compass. Okay, the compass would follow the direction of that field. So that's if the current is flowing upwards. If the current is flowing downwards, still right-hand rule, now you can see that the field is turning the opposite way. Okay, so right-hand rule number 1 is for a straight current carrying wire. So this example that we have right over here, if you had a field pointing in this direction, counterclockwise, around the wire, what direction must the current be flowing then? Well, if we use our hand and simulate a counterclockwise direction of the field, then upward would be the direction of the current flow. Now, to say upward, because we're trying to draw this two-dimensionally on a page, to say upward or out of the page, we're going to use a dot. Because if you look at an arrow, so if someone was shooting an arrow, perfect arrow, if it was shot at you, the first thing that you would see is the very tip of the arrow. All you'd see is a dot coming right at you. Now, if this arrow is being fired away from you, the last thing that you would see moving away from you would be its fletchings, or an X. Okay, so the way that we say toward you is with a dot, and the way that we say away from you is with an X. So this one, because we've said that the current must be flowing out of the page, we draw a dot in there to show that the current is flowing outward away from you. Okay, so if you put your hand on the page like this, you should have your fingers following the arrows on the diagram, and so your thumb is going to be pointing upward. Now to say upward or out of the page in this case, we use a dot. The other one, the magnetic field is pointing the other direction, and so to make that happen, or clockwise, my fingers are going to curl in this direction, and so my thumb is going to be pointing down or into the page. And so I have an X then, an X to show away from me or into the page. Rule number 2 is for current carrying loops of wire. So really where this is important is with solenoids, like this. So this is just a whole bunch of loops of wire all coiled around a tube of some kind. So this right-hand rule is going to help us figure out which is the north pole and which is the south pole of this coil of wire. But it's going to be a little bit easier to work with just looking at a single coil of wire. Okay, so this is what we're talking about. Single coil of wire. And if you look on your diagram below, that's what it looks like on the page. So when you're figuring out the direction of the magnetic field using the right-hand rule for a loop of wire, it actually could work the exact same way as the first rule. Imagine that this is a straight wire. It's just a long wire like this that has been curled together. So if your thumb is the direction of the current flow, your fingers will curl in the direction of the magnetic field. Okay? And so let's say that if current is flowing this way around the wire, then your fingers are going to coil inward. Okay? Your fingers are going to coil inward. And no matter where you go on this wire, your fingers are always going to coil inward. So that tells you that the magnetic field produced by this coil of wire is going to really just point through the wire this way, up and around, and back this way. Remember that magnetic field lines are always loops. Okay, so it's going to point into the coil, around the back, and back inside the front. Okay, if we were to go the other way, using our thumb as the current. Now, our fingers would be coiling around the loop this way, towards you and then back around. So if you use your thumb like that, you'll notice that the same thing happens all the way around, and so the field is pointing out of this loop of wire and then back around this way. Okay, we have a short form for that. It's a little bit easier to do with your hand, just more convenient. So you can imagine that if current is traveling this way around the wire, your fingers would act as the current instead of your thumb. So the other right-hand rule, we were using your thumb as the current, which you still can if you follow what I just said. But if you can use your fingers because they're easier to curl, and then your thumb would point in the direction of the magnetic field. Okay, so if we did this using our normal right-hand rule with your thumb as the current, your fingers are pointing into the loop, which tells you that the magnetic field is pointing this way. If you use your fingers and your thumb, your fingers are the current, your thumb is pointing back towards you like this. That tells you the same thing as the original rule, okay? That the field is pointing this way through the loop. Now for the example on your page, it tells you that the current is flowing clockwise, or this way. Ooh, see if I can do this with my right hand. It's flowing this way, and so my thumb is pointing outwards. Okay, so on your page you'd be drawing an X. It doesn't really matter how many X's you draw, you're just showing that the magnetic field is pointing inward. Okay, but when the magnetic field points inward inside the loop, then it's going to go through the loop and curl back around, right? And so on the outside of the loop, you should have a whole bunch of dots to show that outside the loop, the field is curling back around. Okay, so just imagine this. Imagine this X is one field line. Okay, so it's going away from you, and then because it has to make a loop, it has to curl back around outside the coil, and so it can return back to the inside. So I'm going to see if I can draw this in a somewhat three-dimensional way. Okay, that's the field line we're talking about. Or we can look at a side view of a solenoid. So what you're really looking at is this, just as if you had cut it in half this way. Okay, and then you peeled away the front, so what you're looking at is all the ends of the wires. Again, it's difficult to draw this in a three-dimensional way, so we use schematics instead in order to draw it. So what this is saying is that current is flowing into the page, over here, into this wire, and it's coming out of this wire. Okay, so if I were to draw this, see if I can, in a three-dimensional way, it would be going like this. It's coming out of this side and going into this side. And then it's coming out of this side and into this side, etc. Okay? Again, difficult to draw, so we use X's and dots to show what we're talking about. Okay? And so in this case, if you're doing the right-hand rule, then your fingers should be pointing into the page on the top and out of the page on the bottom. This is my right hand. And so your current is going to flow, so your magnetic field is going to run this way on the inside of the solenoid. This way on the inside of the solenoid. And then it's going to go like this and curl back around, just like a bar magnet. Curl back around this way. Here's all our field lines. Okay, and you also have these smaller loops over here, just like we would with a bar magnet as well. Okay, so a solenoid has the same type of magnetic field as a bar magnet. Now, it's important then that you notice that since this acts just like a bar magnet, it has a north and south pole. So if the field is pointing this way inside the solenoid, but back around outside the solenoid, that would make this the North Pole and this the South Pole. Go back and look at magnetic fields for bar magnets to confirm that that's the direction that magnetic fields point for them to. Here we have a comparison of a bar magnet and a solenoid, or the fields around them, and you can see that they're pretty much the same. The only difference here is that there is no inside of a bar magnet, though we see the field lines passing through the inside of the bar magnet and continuing outside, which is totally true. We just can't access the inside of a bar magnet. It's kind of solid. With a solenoid, there is an inside of it. And so where the field lines are still loops that go through the inside and all the way back around, now we can access the inside of it, which means that those field lines, which are usually the densest ones, are available to us to use in some way technologically. Okay, you also might notice that the bar magnet seems to have more field lines, seems to have denser field lines than the solenoid, but that's not a general rule at all. So we said earlier that if you put more current through a solenoid, it creates a stronger magnetic field, which would mean more field lines in the diagram. So that's really just not a difference. Okay, now finally, there are several ways to change the strength of an electromagnet, to change the strength of the magnetic field that a current is producing when you run it through coils of wire. Number one, you can place a ferromagnetic material inside the solenoid or inside the coils of wire. So if you remember when we put those two steel bars inside the solenoid and clicked them together, they were really difficult to pull apart. That's because there was a field inside the solenoid, but then when we put those two ferromagnetic bars inside the solenoid, their domains lined up and started creating their own field as well. Okay? And because they're creating their own field, it adds to the field that they're already in, which creates a stronger field. So if you wrap a wire around a nail and then run a current through it, it's going to be a stronger magnet than if you just coiled the wire around air. Okay, so use a ferromagnetic material, that'll make it stronger. You can also increase the number of coils that make up your electromagnet. So I said that the solenoid that I was using was a triple layer solenoid, which made it stronger than other solenoids. Okay, that's just because there's 3 times the number of coils as there would be on a single layer solenoid. So running the same amount of current through both of those different solenoids, the triple and the single, you'll get 3 times the magnetic force, 3 times the magnetic field from the triple layer solenoid. So more coils makes a stronger electromagnet. And finally, a greater current. If you remember, when I turned up the voltage on my voltage source, then it became more difficult to pull those two ferromagnetic bars apart. That's because a greater current creates a greater magnetic field and more magnetic force. Now, one final note. You'll often see current referred to as conventional current. That's because we consider that current flows in the direction of positive charge. Now that's not really how it works. Electrons are the ones that are flowing when we've got electricity going, and so it's really negative charge that's flowing when you've got electric current. But the convention is that the right-hand rules work with the flow of positive charge. Again, positive charge doesn't flow, but if you imagine that the positive charge was the part that was flowing, that's what we're talking about. So when you use the right-hand rule, your thumb points in the direction of the current for a straight wire, and it's pointing in the direction of positive charge flow. And so if the question that you're doing is talking about the flow of electrons, you have to flip your hand around. So your thumb would not point in the direction of the flow of electrons, it would flow in the opposite direction. So that's just something to keep in mind.